In this next section, we're going to look at exponents and radicals and properties that are used to simplify those types of expressions. Some of these properties will be later used when we go to solve equations that involve exponents or radical expressions, but for now we're looking at just simplifying expressions that contain these. Okay. To start off, let's start with the definition for exponents, and that is, if I look at a to the n, this is just a product of our base a n times. Okay, so I'm going to take a number and I'm going to multiply it by itself that many times, whatever that n is. In these cases, n is a natural number. So, for example, if I said a to the fifth, this is a times a times a times a times a. If I said 3 to the fourth, with the numbers we can take it and actually put a value to it. For the variable expressions, we're probably going to leave it in the exponential form. But if I see something like this, then I can write it in that exponential form. Okay. These next two are actually part of our definition. A to the 0, so again I said n we're going to choose to be natural numbers, but if you ever have an exponent where it's 0, this just means I'm looking at a 0 times. It's not 0 because then if I multiply that, I'm not going to get anything, but I do want to define that 0 power to be 1. Okay? And we have a better look at that later when we get into exponents and logarithms. There's a reason we don't want this to be 0. And again, if we think in terms of undoing our multiplication, we need that to make sense. Okay, so that's why this is not going to be 0 here. And of course, a to the 1 is just our a, whatever our real number is. Okay. These other properties are again mostly to simplify expressions. So if I look at a to the negative n, anytime I have a negative in that exponent, this is saying I'm going to take 1 over a to the n. Okay, so it just moves it from one place to the other. Okay, if it's in the numerator, it'll go to the denominator and vice versa. So note, if I have 1 over a to the negative n, this is the same as a to the n. Okay, a to the n times a to the n. So if I have two different exponential expressions, but the bases are the same, and the exponents are different, then all we're going to do is add those exponents. Okay. Now, just like our distributive properties in prior sections, we can see that if I have an exponent being applied to two or more factors, then I can distribute that exponent to each factor. Okay. Just like here, if I have two expressions where they both have the same base, then dividing these means I'm going to subtract the exponents. Order again does matter because subtraction is not commutative, so whichever one is on the top, that's the one that's going to be first. Okay. Another way to think of it is if it's in the bottom, that's the same as a negative exponent. So that's why I will get the subtraction of the bottom one. Okay. And again, like we said, it's going to be distributive over the operations inside the grouping symbol. So if I have a division, I can distribute my exponent to both the top and the bottom. Okay. Some other properties, oftentimes you'll see an exponential expression raised to a power. Here, this just means I'm going to multiply both of those powers, because it's taking that expression times itself that many times. So for example, here if I looked at 2 cubed squared, this means I'm looking at 2 cubed times 2 cubed. And again, like bases, I'm going to add the exponents, which is 2 to the 6. Or I can think 2 to the 3 times 2 gives me my 2 to the 6. Okay. Here, again, I can distribute. So that negative power can go both to the top and bottom, just like in this last case. But the difference here is I've got a negative exponent. So to simplify, I want to get rid of that negative. So here when I do that, I'll have an a to the negative n, which means that's going to go in the bottom, and b to the negative n, which is in the bottom, so it's going to go to the top. Okay, so notice there, I changed the sign on my exponent, but I also changed the position of my bases. Okay, and then lastly, same thing, if I have an a to the negative n over b to the negative m, this one's going to do two things. So again, I have those negatives in there, which are going to change the position of them, so I'm going to have a b over a, but again, I've got some different numbers in there. Oops. So we would get that. The last property we're going to look at is scientific notation. And this one's not really a property, more of a definition for another way to write numbers. For this class, we will use scientific notation a little bit in a couple of the different sections, mostly when we're looking at applications and we're trying to solve them. Some of the real-world applications that we look at have really big or really small numbers, and scientific notation is great for those. Outside of this class, when you get into some of your other classes, scientific notation is going to be used quite a bit. One of the great uses for scientific notation is to round things to correct places. So if you want a solution to a significant number of digits, we use scientific notation to determine where those digits are. Okay. Our definition for scientific notation says that a number, whatever that number is, can be written as a times 10 to the n, where a is a real number between 1 and 10. And more specifically, I'm going to put this in color here, a should be a natural number. Okay? We don't want so a should be a real number. More importantly, it's usually going to be a decimal. Okay? We want a to be between 1 and 10 because we want the decimals to be small. I don't want to get a scientific notation that looks like 30 times 10 to the blah. I want it to be some nice number, between 1 and 10, times some number to an extreme power. Okay? And so some examples of scientific notation and how it works. So like I said, it's going to be used for very big or very small numbers. Okay? And so to put a number into scientific notation, the first thing I need to determine is what is my a. So what is the number between 1 and 10 that I'm going to use so that I can rewrite the value of this. Okay? And so the nice thing about the 10 to a power is it takes care of all those extra places. I've written these with zeros, but you can have other numbers here. So if I've got a huge number that's in the billions, it doesn't matter if it's all zeros out there. It just matters what those first couple of numbers are, because then I can round it off to a significant number of digits. Okay? So in this case, I'm going to look, and my two main numbers here are 5 and 2. To get that between 1 and 10, I'm going to think 5.2. There's my number between 1 and 10. And then, to get the number n, my natural number that I'm going to use for my power, I'm basically just looking at how many places I had to move from the end of that number to the place where I want to put the decimal point. Okay? So in this case, you can think 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So this is 5.2 times 10 to the 9th. Okay? For really small numbers, I'm going to do basically the same thing. And again, I could have things other than zeros in here. Usually for the small numbers, these are going to be zeros. For the big numbers, not necessarily. Okay? But again, I'm going to start by looking at the numbers that I have and putting it between 1 and 10. So here 1.3 will be between 1 and 10. I can't choose 13, okay? And I can't choose I could choose 0.1, but no, I can't. I can't choose 0.13 because that's going to be less than 1. So 1.3, and then same thing. I want to put the decimal there. It's already right here, so I just need to move it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. The difference here is because my number is very small, and I'm moving my decimal to the negative direction, I'm going to have a negative exponent. Okay? So there's my scientific notation. How to get it to a bigger number, it'll be positive. To make it a smaller number, make it negative. So now that we've looked at exponents, let's look at the other side of that, which is the radical expressions. And to start with that, if you recall, we said that if I look at a to the negative n, that was 1 over a to the n. So it gave me a rational expression. But we didn't really talk about what happens when I look at a rational exponent. Okay? So if I look at something like a to the 1 over n, okay, this is basically saying I'm taking the nth root of a. So it's our definition for what we mean by a radical expression. Okay? For a to the m over n, this means I'm looking at the mth power of a, so a raised to the m, but then taking the root, the nth root of it. Okay? And here, the nice thing about your radicals and exponentials is it really doesn't matter what order you do it. Some cases it'll be easier to work one way or another, so I can say this is the mth root of a to the m, or I can say it's the mth power of the nth root of a. Both of those mean the same thing, and it just depends on which order you want to do it. Most cases you're going to want to take the root first and then exponentiate it because you're going to be dealing with smaller numbers. But you can work either way. Now, this one is a little tricky. This is another one of those properties that kind of throws people off sometimes. If I'm looking at the nth root of a to the n, it almost looks like those roots and powers should cancel out and I should just get a. Okay? And that's true in some cases. This one actually has two different solutions, and it depends on what my n is. Okay? So if n is even, let's actually start with the odd. If n is odd, so if I'm looking at the cubed root of, say, a cubed, then this is just going to be a. Okay? So again, my example there, cubed root of a to the third is just going to be a. But if my n is even, so if I looked, for example, at the square root of a squared, here there's actually two values I can use, right? Because if I look at negative 2 squared, for example, and then took the square root of that, I'm going to get 2. But if I took 2 squared and took the square root of that, I also get 2. So here, I'm actually going to end up with the absolute value of a. Okay? So here you have to be a little careful. If your n is even, you actually get an absolute value sign on there. If it's odd, it's just the number. Okay? Our properties that we had for exponents where we distribute also work for our radicals. So if I had an ab all under a root, this is the same as the nth root of a times the nth root of b. Likewise with division, this would be the nth root of A over the nth root of B. Okay. And our power to a power works as well. If I'm looking at the mth root of the nth root of A, say that a couple times quickly, that basically combines my roots. So this is the nth root of A. Okay. This one, it doesn't quite always sink in what we mean by that. So for that, let me give you a concrete example. If I had, say, the square root of the cubed root of 64, okay, this means I can combine these roots. So again, square root, think 2 and 3. That's going to be the 6th root of 64. And then I can simplify that down to 2. Okay? And if you don't know how to simplify that yet, that's okay. We'll get there. Remember those, though. So that's all we mean by that last property down there. Okay? A couple of things to note with your roots. Square root of A equals B. And I'm going to introduce some notation here. That double-headed arrow, that means if and only if. Means when I'm looking at that double arrow, I can read it either direction. Okay? So if the square root of A equals B, then B squared must equal A. Okay? In this case, B does need to be positive. Okay, because I cannot have a square root equaling a negative number. So my B, and I do actually mean greater than or equal to 0. B must be greater than or equal to 0. But this also says if B squared is equal to A, then B has to equal the square root of A. Okay. Likewise down here, if I'm looking at the nth root of A equaling B, this is also an if and only if. This tells me that B to the n has to equal A. So if the nth root of A equals B, then B to the n equals A. This is true if B and A are both greater than or equal to 0. If your B or your A happen to be negative, then you have to be very careful about what your n value is doing. Okay? So even roots versus odd roots of negative numbers are very different. So here for A and B both being greater than 0. Okay. So there's all of the properties for both exponents and radicals. Again, some of these you'll be using to simplify expressions, but you may also see these later on when you're solving equations.